This is Hacking.NET Applications, Reverse Engineering 101, the basics of going up and reverse engineering. Well, welcome to AppSec. I'm having a great time. As always, Jon McCoy. You can find all my stuff that I'm showing here at digitalbodyguard.com. The research is open and free. The tools are free and make themselves open. And like I said, Digital Bodyguard, you can find all of my past talks that go into everything I'm covering in much more detail. So reverse engineering. You're going to look at how much time it takes, the skill and effort involved, and the countermeasures. I'm not going to be talking about the countermeasures in this speech, more just going in there and doing it, what you're typically going to find. This is a typical application overview. When you're looking at the application, it has 15 threads, 90 classes, and they're just huge mammoths. And in the old days, you might use IDA Pro or some other technique. This is looking at .NET, where you need something that scales and works in this new paradigm. Let's look at something real quick of like reverse engineering is like a black box analysis. This is a update mechanism for an application. I ripped out its update, so I wouldn't necessarily have to show what application this is from. This is Grey Wolf. It's a type of decompiler. Instead of decompiling, it's an editor. Instead of trying to round trip through source code and put it back, this is, in the real world, I want to change something. I want to affect an executable or DLL and deploy it quickly. That's what this does. It's not technically a decompiler, but if you don't know, .NET, along with every other programming paradigm that's ever come, the deployable is source code. You can go from a C++ app back to source code. You can go from assembly code back to assembly code. This is .NET going back to .NET. You see over here, this is IL, and this is source code. So this is an update mechanism. The application phones home and pulls down a new version. So you look at a file downloader, and what does it actually do, right? Here's crypto. It's crypto algorithm, and it does decryption. You can say, okay, it's doing fairly good crypto. It's initializing all of its vectors. It's going through the proper things. This is what good crypto would typically look like. And that's where you get into stuff like this, where here is the keys to the crypto. So when this pulls down a new version, this is how it secures. It says that this is a valid. So if you're able to sit on the network and say, here's your new payload, you can push this across the entire enterprise with these keys. And this is where we can, as security experts, we can say this is weak because you're not doing asymmetric. This is weak because, and that's what this gets you. This ability to look inside and say, you're weak because. And if you're a pen tester or even a developer, this is some power to be able to say, we need to upgrade. Let's look at, for the malware analysis side. This is Grey Wolf, again, malware, antivirus.exe. We'll import it. And like I said, this is a decompiler that is built for attacking. So this is the same malware imported twice, just to show you. So this one, I went through and de-obfuscated it because malware authors are typically obfuscating and protecting their applications against reverse engineering. So when you look through here and you look through here, this is the difference of what you're looking at. Over here, you're seeing proper names, and you're seeing usable information, and over here, you're seeing obfuscated gibberish. That is a factor harder to read through, right? And so that's de-obfuscation. When you obfuscate your products, you need to know what obfuscation can be undone. You need to actually go in and see if you're properly obfuscating. When you're going up against malware, you want to get inside, you want to be able to go to where the malware phones home. And down here is the save button. You click save, you save it out. And now you have a deobfuscated version of this. You can take this deobfuscated version and go in and apply your changes arbitrarily. So this is the IL. Typically in my speeches I'd go through and show you how easy it is to edit it, but you can quickly get in here and modify the malware to send to drop all tables or ping home or whatever you're looking for in it. But let's look at that. Let's look at what it takes to change something real quick. I'm trying to cram a whole other speeches just to bring you up to speed of what's possible into a quick demo so I can get on to the rest of this. Here's an application. You run it. So this is an off-the-shelf keylogger. It takes a password, and then it will run silently in your machine, keylogging. That's what it does. Drag and drop it over here, and come down to U, function AF, and then here is the logon sequence. You take an input password, you compare it to a known password. That's a login sequence. Come down here to this line of IL, which is an if statement. It's a branch on false, becomes a branch on true. Putting a not before the password validation. Save it out. So I've edited the core logic of the password validation. And now any password validates. So that's being able to reach in, not decompile it, but reach in and edit it. Take that one step farther. Take this function, come up to the top, add a call, select your target. The call basically targets a function inside of your application. Instead of targeting something inside the application, I'll drag and drop a new payload inside of it. And now we have an external payload inside of our target. Lock onto it, say we want to call this function in our new payload. I've added a new payload inside of the target. So now at this point, the new payload is part of the application. When it does that password validation, it now starts this. And so this is how you can quickly round trip deploy, which is good to know that people can do this easily to your application. And so that's kind of the last couple of years of my focus. Looking inside of applications, really being able to say what's in there and give access quickly. This is going to look at reverse engineering of a rootkit lifecycle, going from introduction, exploit, and attack, and being able to look at each step, reverse engineer it, and have a little insight, be able to start saying this is what happened, this is what it would take to mitigate it or detect it, would be the end outcome. So here is the entire round trip. I'm going to go into this in super slow motion for the rest of my speech, but here is the attack vector. You take this executable, that is say it's your product, right? You ship this executable, someone comes and looks at it in a typical decompiler. This is ILSpy, a typical decompiler. You save your source code, you save it out to here. So this is a typical what someone would do when they're reverse engineering your product. They open it up in Visual Studios, now they have your source code on disk and they start doing their typical round tripping. That's where my research comes in, is leveraging exploits and going after them. So someone comes and looks at your source code and opens it up, right? They then come in here, they look at your main app, click OK, and they look at your about box. Okay. They look at your about box, and then arbitrary code runs on their system. It uses a known exploit to get past the UAT, gain administration privileges, drop a rootkit, and now when you come over to PowerShell, you have this going on. So going from they opened your application to rootkit owning them. I'm going to cover this in slow motion all the way through, but that's using a known exploit in Visual Studios that has been around since 2004. There's no plans on fixing it. And you can find and exploit stuff quite quickly when you can read through and see the source code. So not only can you reverse engineer, but you can find exploits. And just to give you an idea of the power of this, I'm inside of Visual Studios, memory space. Come down to payloads, add this in there. So this is a bootloader that was part of the payload. The bootloader loads other arbitrary payloads inside. I can take this and I'll cover it in another one. Okay, so you have this arbitrary code execution inside of Visual Studios, 2 GB footprint in memory, AV's not scanning it, it's a valid Microsoft product, you're good to go. You can grab their developer keys, push it to the SVN, all that. And that's what we're looking at. What does it take to go from exploit to rootkit and reverse engineer it? You have the exploit in Visual Studios. That I'll cover that exploit real quick. So the proper exploit that I used was inside of a user control on a form. It turns out that Visual Studios decided that they would go through and execute the code of every constructor of every user control inside of Visual Studios, not mitigating the rights of the thread or the app domain that it's running in. They would just execute it as pure Visual Studios rights and authority. So here in the user control is the constructor. I spin up a new thread. I look to see if I'm in the application that I was deployed in. If I'm not, I start attacking. And it's that simple. You just add this to your constructors of your user controls. When they look at it in Visual Studios, you own them. So that's the exploit. So when you look through applications, you know what to look for that exploit. The user control is infected. When it's viewed, runs malicious code, and that's where you get exploited from. Pretty clean, pretty easy. Once you find one hole, that's how you get in. The code then infiltrates Visual Studios. It doesn't need injection. I use pretentious names, UAC bypass, which elevates past UAC with injection of whitelisted processes. This is something that's just nice to know about, that pretentious names injected and infected the management console. So over here, this is where the rootkit first got its hold. You click on manage, it executes this and it runs it as an administrator. So, right. So this is bypassing UAC and running it as an administrator. Here is the payload that I deployed. So you open up the malicious payload with Grey Wolf again. And so in assembly code, the payloads were typically small and efficient. In .NET, we have a level of power that we're able to do more complex things. So in my unpacker, this is what I'm starting to see in typical malware that's coming out in .NET. Okay, so here's main, here's the unpacker, here's decrypting it. So this is what I'm typically seeing inside of malware that I'm seeing in .NET. You're seeing high-level usage of crypto. So where you would use that public and private key crypto before, you would use the same thing here. Let's see. Okay, so in assembly code, you would typically try to do a little bit of polymorphism. You would change your signature. In .NET, you can repack yourself in multiple ways. Some of the ways that, advanced ways that I've found to pack and unpack yourself is with assembly code. This is the ability to, just if you're .NET developers, it's kind of nice to know about the assembly code option in .NET. So you can take anything, whether it's a C++ compiled or a .NET compiled chunk. You can allocate some virtual memory and then memcopy in there and put in pure machine code. And this is kind of nice if you're going up against typical malware authors that have old payloads that they got from the old days of assembly code, that they'll repack this and put it inside of their .NET malware. So where they would have done a reverse shell, you might find an assembly code reverse shell. And let's walk you through this real quick. So when you come in here, just to get into the nitty gritty, you do a virtual alloc of some memory that's usable in code space. You do a Marshall copy to take this assembly code byte array and copy it into that memory. You take it through a function pointer and create it through a delegate, and now you have a proper delegate to that memory space that you just loaded with that, and then you simply fire that as a proper invocation of a delegate. And then you're able to execute. I did a step into, you couldn't quite see it. So at that point, you're able to run pure assembly code and execute a message box or execute any arbitrary assembly code. Something to note for reverse engineering is this is completely out of the Microsoft security sandbox of .NET. This is down in the assembly code level, so there's no vetting of what it can do, rights and management, that kind of thing. So you're completely outside the model. And this is why the malware authors typically like to do this. Because when you're outside of the model of the security framework, you're also outside of the model of typically AV will say this process has no rights, therefore I don't really need to care about it. And with this, you can take a process with no rights and elevate it to pretty much anything you want.
Wouldn't address-based randomization forbid this particular capability?
Yes and no. You have allocated virtual memory, which is pointing to a place in memory, and then you're injecting a byte array in there. So in between allocating it and injecting the byte array, you would be vulnerable to that randomization. So for... Well, once you inject into that memory space and you have your byte array, if it moves that, it's a proper function at that point. .NET really thinks it jitted a function and created this. And so if it does move it, you have a proper delegate to it. And yeah.
I don't think you're understanding my question. How can they simply code call message box if it doesn't have an address?
It actually creates an address with virtual alloc. It allocates some memory. Okay. It's quite stable. There's only a small fraction of time in between me allocating the memory and then copying into that memory where it would be vulnerable to address space randomization. After that, it's a proper function. .NET really handles it as though it was a true function and a true delegate to that function. And the message box is properly referenced as a class and not a address location. Also, just as a real quick aside for people that are knee-deep into it, I edited the management console to get a rootkit in there. It's properly signed, and I edited it, so that should have broke the proper signing. However, Microsoft turned off the proper signing check. So by default, they don't check to see if it was properly signed. So you have a rootkit inside of management console that is running as admin, and now you can run your next exploit from there with admin privileges as a Microsoft product. And that's where the attack against PowerShell came from. So once you have that, yeah?
Are you saying signing in terms of like the security catalog or signing in terms of like strong name?
Strong name. And it actually makes a lot of sense why they turned it off, because you would have to hash your entire DLL structure, and you might have 50 megabytes of DLLs. Every time you boot, you would do a full hash. And so when it comes down to it, it's impractical to do hashing of everything you run, which is unfortunate, because you can do something like this where it comes in and it migrates from that admin space over to PowerShell and starts recoding your PowerShell. And at this point, you have a keylogger or your malicious software inside of PowerShell not system level, so AV is very reluctant to find it. And let's look at what it takes to take PowerShell and turn it into an infected process. Find. So here is the infected PowerShell payload, or infector, I guess. The only part that I've come up with for writing good malware is don't put the word installer in the name of the process, because Windows will identify that and help you and kind of mess everything up. So typically when I do my research, it doesn't take too long that my stuff will start getting signatured. That's why I went with the packing everything through a crypto key. And the crypto key comes in and, now let's just run it real quick. So I started coming up with this where the crypto key was stored in the GUI, so you could have a number of payloads or unknown payloads put in the crypto key or different crypto keys and run different payloads. If you're getting signatured and you do crypto against it, it just blows all of the signaturing out of the water. And so when you attack an application, you don't need to attack it in the directory it's running from. You need to attack it in multiple places. You need to attack the native image that's compiled. You need to attack it if it's cached into the GAC. And there's all these different places you can attack it. This is specifically interesting if you're doing reverse engineering. You don't want to focus on what's in the directory. You want to open up a process explorer, see where it's running from, because you can infect it all the way down the line. Your directories can be whitelisting just fine, but the cache up in the GAC is infected. And since you switched out the proper naming and you edited it, it thinks it's still using the proper cache. And so you can infect all the way down the line, and if you're trying to hunt malware, you need to check all the way down the line. So, just as a quick aside. So, this comes through and it updates PowerShell. I attacked the GUI of PowerShell, and this started out as just an office prank, because it was like, okay, look at how lead I am. I can work in the matrix, and it still works. I edited just a couple of lines in there. It's completely stable, and now people can't look over your shoulder or something like that. If you know what you're coding, then you can work in this. That's where this originally came from. And let's look at exactly how this powers. I'm taking this really nitty-gritty, so unless you're really into security or developer, this is going to be a little painful, but this is reverse engineering. So let's look at exactly how this gets in there, because it's like, yes, okay, that's magic, that's nice. So I put down here the two paths that you're going to attack. You unpack. Like I said, it does all of that proper crypto. Okay, and so here it is. Here's the entire attack sequence. You come into this directory. This is in the GAC MSIL, which is neither 64-bit or 32-bit. This is pure IL. It comes into this directory, console host for PowerShell from Microsoft. It enters that directory. It then looks for proper hashing to find the right one. So this is the hash of the DLL, or executable, that's tacked onto the end. You look for each file, and if it ends with something specific, we're going to affect it. You take the original console host and move it out of the way. So again, this is in the GAC, which is the cache. So you're affecting something that won't mess with whitelisting your program files or anything like that. So you come in here and you find all of your input targets. So we picked what we want to inject in there, the different speeds of the matrix or keylogger or whatever you're looking at, and we put it back. We put it back in the proper directory. And so let's consider this real quick. Here is, let's see. Here is the actual source code for the showing the code on the matrix, right? Here is the code. It's just iterate through, show some lines, and here's a typical shim that I use in .NET. You have a void, static, public, and it takes in your target. So I injected into the PowerShell. I inserted this single line like I did before where I called my own payload. I called my own payload and I passed in a reference. So I gave it access to what it wanted, and then I proceeded to attack that object. So this is an object level attack. You're not going after pointers, you're going after proper objects. So if you're replacing, say, a SQL object, and you want to man in the middle a SQL object, this is how you do it. This is how you do it in code. You can also, if I have time, I'll show you how to do it in memory. So you pass in this shim just like I showed you before, and that's how you execute this attack. Let's look at that. So this is the DLLs. Here is, this is the PowerShell DLL. You look at Microsoft PowerShell console host. And so just like we were looking at the malware or the other applications, you can look at the legitimate source code for PowerShell, which is a level of power that's quite handy. Here is the static constructor, the CCTOR, and this is the constructor. And this is the line. This is the line that makes it from regular to malware. So if you're doing reverse engineering and you're trying to hunt down how was this infected, this is what you would eventually come to after a couple of hours. And it's pretty benign, right? And here's how you put that line in there. You insert a line, you put a call out, you select it, you drag and drop your malicious payload, and you run your shim. And it takes an object. My favorite thing in the world to do is put a load arg0, which is always a this. So you put a load arg0 and you put your shim in there. And so you pass this over and then you can attack this. And that's all you really need. You can jump into Visual Studios, write your exploit, or editing, whatever. There it is. And so, as you can see, if you wanted to put a keylogger in there, you could write a library, put that one little shim in there, ship it out, put it in the GAC, put it in the cache. It's still whitelisted just fine, and you have an end-to-end exploit. You find some arbitrary exploit, that, such as that update mechanism that I showed you before. So you have the crypto keys to send an update to an application. You then push that to the entire enterprise, and you're able to do a mass distribution of your exploit across an enterprise from having a couple of crypto keys. So you can go from application to exploit to application to exploit and distribution, and keep that cycle going. And maybe, as you can see, adding this shim into Microsoft PowerShell took a couple of seconds. You click save and you're done. You can develop and deploy this in a matter of an hour or two. So we're not looking at severe teams with polymorphic and years of experience. We're looking at a high schooler with a couple of hours of free time that's able to just totally own core Microsoft. And so the threat level is dropping. When you're looking at applications, these are the points that you want to go after, or protect or verify. If you're looking at a phone home, who is it phoning home to? If it's doing crypto, you know they're blowing holes in their firewall and their IDS to send it out, so it's doing a phone home. You can point that phone home anywhere else, and you can pipe out for data exfiltration. You're using secured dongles. You didn't write your own secure dongle, you imported a library. And it comes down to a single check inside of that library, whether the dongle succeeded or failed. And so anyone that uses that dongle uses this library, you can overcome that library in a couple of minutes, just blow right past all their security dongles. Or in some dongles, infect them, and actually make infectious security dongles, depending on what you see inside of them. And the crypto, just chop it off, replace it with your own, weaken the crypto, and it's very nice to be able to take someone else's crypto or communications algorithm and just have your own pre-canned one that you put in there. So it phones home to your server sends them a new payload, and then you can deploy this on any update that you find in a couple of minutes. So what's next? Like I showed you, running assembly code, and here is what's coming up next after all of this. This is Armitage. JavaScript or a Metasploit Java. So this is a front end to Metasploit. It's written in Java. I converted it with IKVM over into a proper executable. I made this into .NET, so now I can inject into it. So you can take Java and .NET, you can take all these applications, I can inject into this one and start using it like it was a pure .NET application. So here is my payloads. I can inject into it. I can drop my payload in there, and I can add buttons to it. I can go through and edit a Java app just like it was a .NET app. And this gives us a whole new level of ability. Because I have a couple more minutes, I'll show you what can really be done with all of this. Here is this. Okay. I have the best keylogger. Open that up. So here is what you can do at memory. Talked about this a lot. You can look at my research for it. So you can inject into this application, put your bootloader in there. Once you have your bootloader, you can open up your payloads. You can drag and drop your payloads into your bootloader. You can add your buttons, all that. You can drag and drop multiple executables since this is loading arbitrary executables. You can put an arbitrary other executable in there into the same memory space. You can load it up. So I've taken that keylogger, I've injected another arbitrary executable inside of it. You could do whatever malicious thing in it, but you can also take this start button, pop it off of here, and add it over here. And so now that you're in the runtime memory structure, your buttons can go through and edit the actual memory structure. So this button still works, it still fires, it goes across memory spaces that are now one. You can take multiple applications, malware analysis tool, vetting tool, anything you want. You could actually inject in your analysis tool into another process, grab a hold of its SQL connections, and start sending bad SQL commands automatically. You can now inject into arbitrary processes and edit them like I showed you editing on disk, much faster, much more powerful, much more flexible. And this gives us the other ability. So this password validation, how do you know where it goes, right? How do you not spend 4 hours hacking it? You add a right click to this that asks that button, hey, what do you fire? And this button fires U is a class function AF. I could have deobfuscated this and it would have looked pretty. Or you can just ask that button, hey, where do you go? There's your validation, there's your registration, there's where you talk to the server, whatever you're looking for. Quickly jump straight to your target, not spend a couple hours hunting around, go in memory, do your reconnaissance, go in disk, do your effect. And that's the nice little life cycle. So I recommend using sandboxes, not necessarily for protection, use them for dissection. They are a great tool. They'll tell you when they're writing to disk, going out to the internet, all that. They're beautiful. Use your virtual boxes, all that. Use a burnable machine. These are the tools I love to use on a day-to-day basis. Process Explorer shows you what you're actually using if you're using stuff out of the cache. File Assassin is really great for if you're attacking something that is in the cache and it's locked. You can go and unlock it, replace it, and then keep going. Firewalls, outbound firewalls are great, and Universal Extractor is really nice for extracting your targets that you want to run. So you don't have to install it, just use a Universal Extractor. It extracts all of the packed installer, and it's nice for round tripping. Like I wrote a Metasploit payload you would find up on my website. You could do that in-memory injection. You can inject into your target process, say SQL Server Management Studio, and you could man-in-the-middle SQL Server Management Studio from memory from Metasploit. So it depends what you're going for. I mean, one of the ways, yeah. But like one of my favorite things in the world that is just, I appreciate is you can take something like this PowerShell, you can drag and drop it in here. This is a text compatible version of this executable. So I converted an executable into text. I came in here, I then type in all that text and I run an executable straight from text. So this is in memory, this came from a keyboard, this is in the memory space of PowerShell, and you're pretty good against AV, you can migrate around, all from a keyboard attack. So you have an automated keyboard, you can type straight in. So, I mean, the ways of getting in are as many as you can imagine. This is post-exploitation, so like once you own something with Metasploit and you're able to send, this is what you would do post that. Or if you're hunting malware and you're trying to pull apart malware, this is that. So this allows you to find 0 days quickly and use them, but it doesn't create them, I guess. Yeah. Yeah.
Well, and you could use this with one of those USB things that actually look like a keyboard, but they pretend to be a storage device.
Uh-huh. Yeah.
There'd be ways you could do it without a 0-day exploit.
Oh, yeah. And, I mean, this is one of those, like, oh, you own the box, you're God. And it's like, well, being God is really hard. And now it's like, you can write malware in a couple of minutes. So it's like, you are able to get into your client, and now you're saying, well, I took over this machine, and now I own it. Now I'm able to put a keylogger in some of their key software. It'll go around AV. You can do it in 15, 20 minutes. You don't have to have a lot of skill. And now you can start keylogging their core systems. And it's just a way to do the same thing that we've always done. This has been around for 20, 30 years, easy. And this is just the same thing, just much easier, targeted at .NET. Like if you're gonna write a keyboard logger in assembly code, like who knows that, and it's painful as shit. And it's right to make it polymorphic, to change its signature all the time, to do a crypto packer, to do a TCP connection. All of that in .NET is cake. And so it gives you all of that new power for the same old thing. And just kind of bringing it back. Like people, I talked to a guy last week, he did this for COM. People for soft ice were doing it for C++. People did this for assembly code. This is the old thing new again. And trying to bring it back, make it look easy, and it's all free, and I'm not selling it. So it's not like IDA Pro that you have to spend $1,500 to go and get a hold of. You can just start pulling apart and playing immediately. I also throw on, and I try and keep ahead of all of the hacking and anti-editing. So all of the deobfuscation, they'll do crypto packers, they'll encrypt all of their resources, and now you can come in here, come over to the resource editor, and start looking through all of the resources and being able to pull those out. You can come into the class view. And for those developers in the room, I put this button so it goes through and it makes the entire thing public. So you come up to someone else's executable, and now absolutely everything in here is public. So I turn off public, I turn on private, and it's private. And I come in here, I turn off private, I turn on public, and it's public. And so you can take someone else's executable, basically public it, treat it as a DLL, and then gain that ability. Instead of spending hours in reflection, this just done. And that's this button. And so I've tried to take everything I do on a daily basis and make it in one tool, easy, round trip, fast. And if you're on a job with a client and they have an obfuscated desktop application and you know their network keys are in there somewhere, in IDA Pro you could literally spend weeks hunting through that. And in this, done, 15 minutes, maybe a couple of hours. But it just drops that bar. And it starts making us more aware as developers that we need to actually make defendable applications and not just rely on it's a secure network. And that's why I'm here at AppSec, pushing desktop application security, because you would not imagine how many applications I look at and the first thing I see in 5 minutes is SQL injection. And then after that, I'll find non-asymmetric crypto. And all of these things that as web developers, we take care of on a daily basis. Desktop developers barely even care. And desktop applications are our bookkeeping software, stock trading software, critical infrastructure, mobile phones. And we need, as AppSec, to push that. And that's what we can do. Like anything you do programmatically, you can undo programmatically. And I mean, obfuscators don't evolve that quickly. So they're using the same thing, but then they add on one more step. And you figure out that step, you undo it. And we can look at the deobfuscators and see how they did it too. And so it's like you can't run from us. And so, but I mean, if you're fighting malware, imagine fighting malware and their deobfuscator is beating you. And now you can't evaluate the malware. Now you can. And like I've had clients where they would get attacked. Someone would reverse engineer, deploy their product every single time they released. They would obfuscate it so they couldn't prove that they were stealing their source code. And it's like, how do you show that someone is stealing your source code? You deobfuscate them, you look at their source code, and you send them a cease and desist. And yeah, 24 to 74 hours, you'll probably see the update to beat the newest Smart Assembly, Obfuscator, and there's only like 20 obfuscators that are worth much, and they all do exactly the same thing. You can undo them by hand once you have that mindset. The best thing that obfuscators brought to the market was they re-implemented the Microsoft's strong key signing. In every single static constructor, they would do a strong key check to make sure that the strong key wasn't modified. They would do arbitrary hashes of different DLLs to make sure that they weren't modified. And they would basically go in and implement security all around randomly, or phone homes and stuff like that. And then you find that signature, you find what they're doing, you go through and you remove it, and you take care of that. And the scariest thing from obfuscators that you're going to find is that it doesn't really get you that much. Here is the malware that you're looking at. This was all obfuscated. All of these names should have been destroyed, right? And it's like, here's main form, and here's proper naming, like mouse down. And you can come through and get a lot of the metadata back about your target and actually put it back in place. So it's not that bad to look through, and it's like, here's the loading function. But all of this should have been destroyed, but it turns out that .NET keeps a lot of metadata. In labels and about the forms, there's a lot of metadata, so you can put all of that back together. And then there's actually longer-term community efforts to go through and figure out what something does and then properly name it. So you don't have the name, it does a SQL, it does a little bit of crypto, and it's like, well, this is a push or whatever. And trying to do a little bit of natural language processing to infer the names. And so this might actually help when you're coming up against a Russian written application, that it comes through and it puts it in English. So, and yeah, but if you come up against malware in .NET, this is a good go-to. This will allow you in 5 minutes to be able to send a drop all tables to their SQL server. It'll allow you to get their crypto keys and go after it. It'll allow you to do what you need to do.
You know, malware detection utilities, they don't detect the fact that you've gone in and modified the IL for a lot of this?
AB?
No, anything you may have, so say Microsoft Security Essentials or malware bots. Right? I'm just asking.
Well, yeah.
Actually, I mean, obviously, if you've rooted the box, then you probably
turn it
work
off
around it. But at the same time, if you're just doing that alone, that action alone, do they not detect?
Well, you have to look at it a couple of different ways. Like, you can come in and just replace one single string that happens to be the phone home, and you can come into that, like, you can come into it and just replace that single string with your server. And so now that malware checks in with you, and then you can see what packets it's sending.
Well, I'm sorry, I'm saying from an attacker's perspective, not from somebody who's defending.
Well,
so say you managed to get a foothold into the system, and then
yeah.
but there is some AV or something running along, and so you then decide to go and try to inject something into a different process that may be monitored by the AV.
Well, that's kind of an ongoing fight. Like, you come up with an injection process, it signatures it, it finds a mechanism, and it watches for those hooks or whatever.
Well, I'm looking specifically at the way you did the PowerShell exploit where you added, you called it shim.
Yeah.
So if you had some sort of AV running it, is that not?
That specific one, I edited the IL on disk, and no. Like, the upside of .NET is it's a compile time, and so its signature can change box to box, and so AV has a much harder time locking onto it. And so it's also easy to do polymorphic, crypto, all of that in .NET is super easy. And so to write something that's polymorphic, does crypto, and does some sort of tunneling for communication in a CNC is maybe 2 or 3 days for a good developer. And then in that C world, assembly code, it's incredibly hard. It's easy. I get signatured probably once or twice a year, depending on how noisy I am. And then to get around it, I change it a little bit. But all of this, I'm not trying to not get signatured. Look at Metasploit, use their
So I'm just thinking
injection.
of that assumption. So
I haven't had much trouble with it.
All right, let's thank our speakers.
Thanks for coming.